Good afternoon, everybody. It's a pleasure to have you here. This is the first colloquium of the new year for the Department of Physics. We will have for people just an appointment each month, roughly speaking, the first Tuesday of each month, roughly at this hour. And it's a pleasure just to start with a really interesting and exciting topic here with Morten, and I leave to Fiorella the chairman status. No.
It's fun. So Morten is a very old friend of us. We met for the first time 25 years ago, probably in Trento, in the City Star. So time passes by very, very quickly. So, well, Morten is a professor at the Oslo University and also at Michigan State University. So he spends half of his time in Europe and half in the US. He is a theoretical physicist and with special interest in computational physics and in theoretical many-body methods with a special reference to the nuclear many-body problem and the nuclear structure. Today he will give a talk on artificial intelligence and machine learning in nuclear physics. So we hope we will learn a lot from his lecture. Thank you, Morten. Please.
You will choose that about that. No. Thanks for coming. I hope you won't be disappointed. It's a great pleasure to be here, as always. It's actually 51 years since I was back in Sicily. So tempus fugit. And I should have come back much earlier. Before. And the talk here is also, as Fiorella said, is part of the celebration for Marcello Baldo, who I guess everybody heard. The topic today is more to give you a kind of pedestrian approach to machine learning, why this is of interest in physics, and why this should be of interest, would be of interest. It's up to you. If I get time, I may say something about education in these topics and how that could be integrated. There's a lot of things going on in integrating quantum computing, machine learning, computational physics in the basic physics degrees on the bachelor degree and the master degree. So if I get time, I may say something about that as well. Now, anyway, feel free to ask questions. Part of this talk is actually based on this article here, and you can actually pull down everything if you just go to this web link. And Fiorella will also send you the slides and the link to the slides if you're interested. I have several references in the slide. By the way, in the back, can you hear me well? I tend to mumble after some time. So, I mean, just let me know if you don't hear well. And you should not put me on the podium because that would be a recipe for catastrophe, okay? And when I say we, that's not an excess of megalomania. It's actually because there are many people. And I'd like to point out some of the people who have been central here, like Jane is now doing a postdoc, and same with Julie. And these are just two brilliant young physicists, creative. And so if you're looking after good postdocs, I mean, these are some of the people to keep an eye on. And then there are many other people, and some of them you may know, like Alessandro Lovato, Stefano Gandolfi, Giuseppe Carleo has been central in this field of machine learning. There was a famous paper in 2017 where we actually had one of the first really applications to solving many-body problems with neural networks. So you could say that Giuseppe, who's now at Lausanne, has actually developed this field, has been one of the main drivers between these developments, which I'm going to talk about today. And since we are celebrating Marcello, and Fiorella said that we met something like close to 3 decades ago, And you will actually recognize many of the people here. So I think the pointer here is not so good. But you can see Fiorella, you can see Marcello here, and then Umberto is here. And we have many of the people who were central in many-body physics. And I guess everybody's familiar with the center in Trento, is a Center for Theoretical Physics in nuclear physics. And this was actually one of the first workshops on many-body physics. They tended to last 2 weeks in the earlier days. And we had something like 50, 60 people being there. And we had essentially everybody who did many-body physics and the different many-body methods. And I think both Marcello and Umberto and Fiorella stayed there for the 2 weeks. And we had a lot of fun together. And you will recognize many, many other people. And there is actually a follow-up from that meeting. We had a paper with Marcello, and there were 2 PhD students. Actually, one of these became a professor in astrophysics. And he hated so much everything he did with pairing that after the PhD, he deleted all his codes. But Marcello has been very persistent in superfluidity and superconductivity, and this is the type of correlation which arise from those have been a hallmark of many of the deep insights which Marcello and collaborators have developed over many, many decades. So when we talk about machine learning and artificial intelligence, there's a lot of things going on. So I will obviously focus on with machine learning. I'm thinking of a collection of algorithms and methods with an emphasis on statistical learning and data analysis, and obviously solving problems like differential equations. So if you're doing meteorology nowadays and you want to predict turbulence with the Navier-Stokes equations, then people do actually solve many of these equations now using machine learning inspired methods. And there's a whole field which has grown out of this, which is called physics-informed machine learning. And that's a pretty hot field, which is rapidly developing. Now, you can look at many of these statements here, and some of them are pretty strong. I'm not going to comment them, I just put them up there. And you can look up the links, everything in blue here, links you can click on it when you have the slides. This is a pretty strong one. In the long run, AI is the only science. I don't know if you agree with that. I don't think I agree with it. If you're interested in a societal point of view, there is an excellent text by Kate Crawford. She's a professor in sociology from Australia, but she's also part of the leadership of Microsoft. And she's studying the societal impact of AI. These are things which I will not say anything about. So I'm thinking about how we can use these methods for physics analysis and looking at physics problems. But obviously, there are many of these algorithms. If you develop a convolutional neural network tailored to recognize images, these are things which can be used in different ways. And you're probably familiar with this company called Palantir. I don't know if you heard about this company in the US. So for those of you who've seen The Lord of the Rings, you know what a Palantir is. And this company actually has specialized on facial recognition. And they actually sell their services to law enforcement companies. But one of the things they did, and this has nothing to do with which side on the ongoing conflict in Ukraine, they used facial recognition of dead Russian soldiers, and then using social media, they could recognize the soldiers, and then they sent an email to the parents. So that's an application of facial recognition algorithms, which can be debated. So when we talk about machine learning, you're probably, I guess basically everybody's familiar with many of these topics here. But I wanted to assume that there are things which perhaps need to be linked. So just to see the wood for the trees. And in the typical problem which we often have is what is called supervised learning. So that means you have labeled data. That is actually an expensive part of it. So this company, Palantir, has actually access to mugshots. Are you familiar with what a mugshot is? So mugshot is actually pictures of criminals, people who've been in jail. And there was actually a project in the 50s and 60s and before when we had eugenics, where one actually was trying to find out whether somebody had a typical criminal aspect. And this was based on mugshots. And these images have all been labeled. There's been a human who's been labeling these images. So in much of the, image recognition algorithms, there's been somebody who's actually been labeling the images, whether this is a cat or dog or whatever. And so supervised learning is expensive. Now, when we look at physics, in many, many instances, what we actually have is tons of data. So high energy physics has actually been leading when it comes to develop many of these deep learning methods. Because when you run an experiment at CERN, you produce every second petabytes of data. And these petabytes of data have to be reduced down to gigabytes. And then the experiment runs for months, half a year. And then you can do the mathematics and you realize how much data has been produced. And this is something which you cannot traverse with the standard algorithms if you want to analyze the data. So clearly this is the more common case which we face when we do the analysis of experimental data. And I will show you some experiments from active target experiments. Some of you may be familiar with what that means. We also have reinforcement learning, which I'm not going to say much about. So I will essentially stay within these two main categories. The type of problems which we deal with are typically classification problems. And then we have regression problems. And then often we have clustering where this is a type of unsupervised data, where we try to reduce the data set into clusters of things which we believe belong to each other. The typical case which we often have as a physicist is normally this one. You want to classify the events from an experiment, or you want to fit a function. Now, the classical machine learning is based on what we in statistics call a frequentist approach. In practice, that means that there is less emphasis on you finding a probability distribution. That means you want to fit some data. You make predictions with the fit you made, and you want to find correlations in the data. So the other approach is what's normally called a Bayesian approach, which means that you are often more interested in estimating the errors, which means you need a probability distribution. And you also want to understand the causations. What is the likelihood of A given B? But we as physicists, we are like Winnie the Pooh. We want both honey and milk, right? So we want to have correlations, predictions, causations, and we want to estimate the errors. So we want everything. And in the community, there's been actually two main trends in the statistics community. And they are like the trends in many-body physics before. They didn't talk to each other. They hated each other in a way. So my many-body method is much better than yours. This is not very, productive. So I'm going to say a little bit about some of these things, and you will recognize many of these methods. The field with Bayesian machine learning is a very hot field. There's still a reason why we deal with the standard deep learning methods, and that's simply because this becomes computationally expensive. So a Bayesian machine learning would mean that if you're familiar with neural networks, you would replace the activation functions with a probability distribution. But that is time consuming to do. So there's always this balance when you deal with machine learning methods, where you have to strike a balance between the accuracy of what you do and the number of cycles you're willing to spend. This is a kind of balance we always have to strike. So I'm trying to give you this kind of more overarching views on the things before we dive into the details. Feel free to interrupt me, by the way. Eh? Don't hesitate. And then we have what is normally called the pre-deep revolution methods. And these are methods before 2010, 2008, roughly. And nowadays, there's a lot of research going on here, in particular on generative models. I mean, you're basically familiar with ChatGPT. For us as physicists, this is an extremely interesting avenue, because it means that we are trying to fit a probability distribution to the data. And one of the methods is actually what Galileo introduced in 2017 with a Boltzmann machine. So you actually use a Boltzmann distribution to make an ansatz for your trial wave function in a quantum Monte Carlo calculation. And in that way, you train a probability distribution to reproduce your data, which actually in this case is data you keep generating, which is the input to your quantum mechanical memory system. So generative models are actually a very hot research topic. But then we have the good old-fashioned ones, which everybody has met in a linear algebra course. And these are normally methods which I would call low-level machine learning, in the sense that the training is extremely simple, just a matrix inversion in the case of linear regression. So let me just take a look at that. Because what you see on this slide is the basic content of everything you do when you deal with machine learning or artificial intelligence with machine learning. There is artificial intelligence without machine learning. Just keep that in mind. Okay. So you would have a data set. That's your input, and then you have the output. You have a model where you can fit a likelihood function if you're doing logistic regression, for instance, or classification problems. Or you can simply have a continuous function which you want to fit to the data. And then there is something which has different names. It's called an objective function or cost function, error function or risk function, etc. And this is a function you optimize. And you have some unknown parameters alpha here. And then you want to optimize this function. And that hopefully gives a good description of the data. So what is a good model is actually a important philosophical question. And that is where you bake in all your insight about the specific discipline. So, and then at the end, at the heart of everything, there is an optimization problem. So let me try to explain to you what this means in terms of things you've seen before. So most of the deep learning methods or machine learning is you combining your knowledge about linear algebra, statistics, and optimization problems. So these kind of fields actually merged into the field of machine learning. And then there is a lot of ad hoc fixing, in particular in the optimization part. And in the optimization part, that's actually a field where you can get many new friends. And I'm not saying that you don't have friends. I'm not inferring that. But this is a field where if you do something on the optimization part, you will get friends which will cite you. That's the kind of friends I'm thinking of. Perhaps not real friends. They may like you because you came up with something. There's a method which is called ADAM, adaptive momentum, which has, since 2014, more than 150,000 citations. A good physics paper is in the hundreds. So that says everything. Actually, this is a field where the average age is pretty low. So if you look now at what enters, this is just back to, I hope you don't get offended if I remind you of some basic linear algebra methods, but that illustrates essentially what is behind all of these methods. So what you would have is an input data, you have some output, and then there is actually an assumption you make about the data. So this is before you make the standard model. So you're assuming if you do a fitting of a continuous function that this guy here is a non-stochastic continuous function, which means also that you can think of that if you have an input to the data set, this is something you would fix. If you're making a survey and the date of birth enters, we are pretty sure that that is not a stochastic to be treated as a stochastic variable. On the other hand, we assume that there is a noise. This is this epsilon here. And that will actually influence the way the probability distribution looks for this one. And this is normally given by a normal distribution. And then you would make a model. And if you're making a polynomial fit, you would define a matrix X where each column represents the polynomial degree of freedom. So if you have a polynomial of degree 10 with the intercept, this matrix would contain all the X's, and then each column would be the polynomial degree. And then you can make a model like this. And when you've done that, you bring back mean squared error, which is a standard way to assess the quality of the model you made. And then you would say that this is my objective function, and then you would optimize this one with respect to the unknown parameter. And when you do that, you get this famous expression here. Anyone's never seen that in linear algebra? This is just the ordinary least squares. And if you can invert the matrix, you're done. So this is the machine learning here, or the training. The training of the parameter, the optimal parameters theta, is given by a matrix inversion problem. So this is a pretty straightforward deterministic one. When you replace this with a neural network, then the training will be done by the neural network itself. But this is just a very simple case, and linear regression is very popular. You will find it in every textbook because you can derive analytical expressions like this. You can find the analytical expression for the variance of the parameter theta. You can make confidence intervals. You can derive everything from a probabilistic or from a statistics point of view. So you have methods like, I can just remind you of this one. This is called the ridge regression. So you have a shrinkage parameter where you can shrink some of the values. So this becomes a hyperparameter you can tune to get better fits to the mean squared error, for instance. But now you're optimizing this function. So as I said, you have to decide on what is the ideal objective function for your problem. It doesn't need to be this mean squared error because that emphasizes outliers, but it could be other types of functions which are more relevant for your case. And then you also have something which is called lasso, which I always forget, the least absolute shrinkage and selection operator. This does not give you analytical expression for the unknown parameters thing. But these are popular methods in linear regression. Then you can make a mapping of your input variables in case you want to distinguish them in some specific way. You have kernel transformations, etc., etc. But this is basic philosophy. So you have these three ingredients: the input data, output data, the model you make, and then the function you want to optimize. And in some cases, you have analytical expressions, but in most cases, you have to do this numerically. And then, to the big surprise to many, and perhaps disappointment, is that you would typically perform a Taylor expansion of this object. You stop at second order. You stop at second order, you have Newton's method. Newton's method is then dependent on the gradients, which will depend on these parameters. And you don't want to calculate the second derivative of this quantity, which is called the Hessian matrix, because you have to invert that one. And if you're doing neural networks, you have millions of parameters. And then you replace that with a learning rate, a parameter. And to update this parameter in the Newton iterations is actually one of the big bottlenecks in machine learning. And that's where you can get many inference if you make improvements there. Because again, this is you striking a balance between the accuracy and the number of floating point operations or number of cycles you want to invest. Any questions? Okay. So I like this field quite a lot. It's actually the most fun course I've been teaching for decades. And I've been teaching for, what is it now? I shouldn't say 5 decades, but it's 4 now, something like that. You can do the math and find my age. So the thing is that this is a field which combines lots of these methods, and a familiarity with these methods is actually, I mean, people now, you have this kind of feeling that if you can spell machine learning correctly, you get a job. I actually had a student, I mean, she was brilliant, by the way. She would have gotten any job anyway. But in the interview, she said she was following my course in machine learning. And according to her, she got the job after the exam. But I think she would have got it anyway because she's a brilliant person. Okay. Now, what I put here is actually a list of references. And there's actually, I wanted to highlight this one. This is actually an extremely pedagogical article. And the thing which is nice is that every example has a Jupyter notebook which you can download and run and reproduce what they have presented. So that's highly recommended. They've done a huge service to the community. So if you wish to teach yourself quickly, this is an excellent read. And then there's Pankaj Mehta. Mehta. The first one. Yeah, the first one. And then Giuseppe Carleo has been the lead author of tons of papers. And then we have some papers. And when I say we, these are papers which we have with students like Jane and Bryce and Giuseppe Carleo as well. And for those of you doing nuclear physics, there's actually a report here, and there are tons of papers. The thing is, with this field, it keeps moving quickly. And you have the feeling that you can barely stay ahead of what is going on. So the thing, this is a field which you, in a sense, can say has exploded due to the advances in high-performance computing as well. So that plays a central role here. Because many of these calculations here could not have been done without you having access to GPUs and CPUs and the best machines. So that's quite important. And you could say then, if you look at in physics, many of the problems we deal with are multi-scale problems. So if you're dealing with turbulence and weather forecasting, this is a multi-scale problem because you have to run calculations with very, very fine grids, but then you also have large grids which are needed. So for turbulence, even if you're using a mean field method like Navier-Stokes, and that would be dubious itself, but you really make the mesh very, very small. And that's a typical example of a multi-scale modeling. You want this to be fast simulations, and you want to quantify errors. You have the machine learning theory methods, you have the data analysis part, and everything is intertwined. So in a certain sense, if you look back over time, this is just one of the tools we would use if we are experimentalists and we do the data analysis. So we did linear regression before, but we never thought of that as machine learning, right? But it's always in textbooks because it's what I would call low-level machine learning. You have a simple recipe for learning the optimal parameters. This is taken from my own field, nuclear physics, and you could actually replace that with any field in physics. I mean, it's this kind of dialectics which kicks in basically essentially everything we do. And you probably heard about the digital twins. Does that ring a bell? So a typical example would be a windmill park. So you have a physical realization, and then you have some software which governs how the windmills are rotating, right? It gets input about the wind speed, the meteorological weather, the weather forecast, etc. And then it adjusts the windmill according to the wind direction. But then the mills have sensors, and they would feed back to the software. And then you keep adjusting the software. That would be an example of a digital twin, where you have these dialectics between the simulation and the real-world implementation. And in essence, when we do physics, I mean, the scientific method is about this, right? We do the experiments, we have some theoretical tools, and then we analyze the data, we feed back to the theoretical tools based on experiment, and back and forth. So in a sense, a digital twin to me is nothing but the scientific method applied. Okay, so there are tons of things. I'm not going to read everything. I hope you can apologize me for that. But there are simply tons of things which we can do here. And if you do nuclear physics, you can often apply this to nuclear systems and conditions that are not accessible to experiment. You can quantify errors. In theory, you can often make these extrapolations, which are extremely useful. You can estimate parameters, multi-scale data sets, model reduction, and many, many other things. So this is a field which simply has exploded. And in a way, it's your creativity, which is a kind of, I shouldn't say the limit, but it's a way to, when you look at many of these things, this can really boost people's creativity. There's a field here which is actually quite interesting, and it's called for fast machine learning. This is actually where this is the digital twin. So this is where you combine software and hardware to actually analyze complicated experiments. Like in particle physics, this is widely used. And there's this paper, if you're interested, by Diana, which appeared in Big Data recently. So they actually have several examples across scientific domains, techniques for training and implementing performant and resource-efficient algorithms, and also how you design hardware for doing this. So this is also one of these many, many emerging fields. Here's another one on accelerator architectures for deep neural networks. So many people who deal with accelerator science are actually using deep neural networks to train the setup of the accelerator. Just examples of what is going on. This is the one about physics-driven deep learning or physics-driven machine learning. And this is a group of people. There's a guy in New York, Kanadakis et al. And they've been dealing with essentially applying these methods to the solution of Navier-Stokes equations. So if you do fluid mechanics, this is actually a pretty hot research field. In particular, if you're interested in turbulence. And turbulence, when we are modeling, shouldn't say that in case of flight anxiety, it's only 10% of the winds which get tested in a wind tunnel. The rest is simulations of Navier-Stokes equations. So 90% of the winds are never tested. And turbulence is obviously very important. So Navier-Stokes simulations combined with the machine learning methods is actually a very, very hot field of research. I shouldn't have said that about, because if you have flight anxiety like my wife and my daughter, I mean, this is the things you have to tell me. Sorry for that. Okay. There's actually I wouldn't say, I wanted to use this one to point to Sofia. Sofia Vallecosa is a high energy physicist who has been working on machine learning and quantum computing. She's at CERN. And there's a link to a very nice video about a recent talk she gave. So this is an example from active target experiments. So there is a experimentalist at Michigan State. His name is Daniel Bassel. Some of you may know him. These are active targets where actually the target is a detector. And these are examples where you produce something like terabytes of data. And ideally, you would like to recognize whether this is a proton event or carbon event and so on. And experimentally, you have a lot of noise. And sometimes it's very difficult to actually figure out what is it. And Daniel told us before we did this paper that he had spent more than half a year with traditional analysis tools to actually figure out what was going on. And in this case, we use clustering methods to actually select clusters of data which we thought were of the same type. And then you reduce the dimensionality of a problem with unsupervised learning. And then you use the traditional methods to analyze the data. So that's just one way of dealing with it. But what I wanted to say a little bit more about is many-body physics, since we also celebrate Marcello. And Marcello is one of our heroes in many-body physics. That's important to keep in mind. And one of the methods which has been very popular and which provides you almost exact benchmarks of the calculations of ground state properties are Monte Carlo methods. So the idea then is that you have a multi-dimensional integral. So this R, if you're thinking of the neon atom in atomic physics, you would have 10 electrons if you freeze out the nucleonic degrees of freedom. And then you have 3 dimensions. So this integral is 30-dimensional. And you wouldn't like to use Gauss-Legendre methods or Gaussian quadrature. You wouldn't do that. It would take the age of the universe to get even a calculation with the 10 integration points in each direction. So you just leave it. You would do Monte Carlo. So you do a stochastic sum. And it means that you need to have some insights about this trial wave function. Because if you have the exact wave function, there's no point in doing this because you solve the problem, right? So you have a guess for what the wave function looks like. And that's the big issue. And what we have done, and many have done, right, is actually to replace this trial wave function with a neural network with some physics diagrams. So let me just say a little bit about it. So what you would do then in this approach is actually to rewrite this integral which you see here, this expectation value, in terms of a standard statistical rephrasing of an expectation value where you define a quantum mechanical probability, the first one, and then you calculate your trial wave function with these parameters alpha as variational parameters. And then you have to you define a new quantity, and then you can redefine the expectation value of the energy as a probability times the quantity you want to evaluate. And then you use standard sampling. You invoke Bernoulli's law of large numbers, and you hope that your average is getting close to the exact average, which you don't know. But this is an integral which has a limit given by the trial wave function you plug in. So you may never get the exact solution. which you can get by diffusion multi-color calculation, which is a way where you can, if you simulate long enough, you can approximate the exact solution to the ground state with a given Hamiltonian. So everything is determined by the Hamiltonian you're choosing, obviously. Then I'm just putting up some of the mathematics here just quickly, just so you get a feeling of the optimization problem. This optimization problem is something you would do irrespectively of whether you do machine learning or whether you do a standard variational multicolor calculation. And in this case, you would take the derivatives of this expectation value with respect to the parameters. And this is your optimization algorithm. So you calculate gradients again and again. And then, since you don't know better, you use Newton's method. And ideally, you would like to invert the second derivative, this quantity, because it's not this energy you want to drive to zero, but it's a gradient. So if you think back to Newton's method, there is a denominator, which is given by the derivative of the function you want to find the roots of. And in this case, this is the second derivative of that function, the gradient, the derivative of the function. And that's the mean object. That's the Hessian matrix. And that's the one you don't want to evaluate if you have zillions of parameters. If you have a small system, this is okay. Alternatively, there's a question to the younger folks. How many of you have taken quantum physics or quantum mechanics? Okay. There is a quantity which is called the variance, which you can calculate. And if you have the exact solution, what should the variance be like? That has a value. So you could actually do your optimization with respect to the variance because you don't know the energy, but you know this ideal value for the variance. So if you calculate quantum mechanical the variance, does anyone have an idea what it should look like? Should be zero, exactly zero. So in my case, this is the number of points which Norway gets when they try to qualify for the World Soccer Championship. Okay, that's a joke. Nobody understood. Anyway, so you're driving this quantity. This is a quantity you want to optimize. This is your derivative, and you have to calculate these integrals. This is the basic recipe. Now, when you do machine learning now, you actually use this as, so the energy as your objective function. And this is the gradient you want to drive to zero. And this is what you train in the machine learning algorithm. But now you replace this trial wave function with a neural network. And this is what has been done. And I just wanted to say something about neural networks. There's something called universal approximation theorem, which says that you can, to a given precision and with one hidden layer, you can approximate a continuous function to a given precision. It doesn't tell you what this precision should be, but you can actually fit a nonlinear function. If you have a linear function, you could get away with just one single quantity here. But if you have at least one hidden layer where you have the training parameters, these are these weights here, these are the parameters you optimize. And every iteration is actually you feeding the network forward with an initialization for the parameters. And then you calculate the derivatives of these quantities in order to get the gradients. And then you train the network in going backwards. And then you go back and forth. Each iteration is just one back and forth. So when you look at the results now, when I say iterations, this is actually one forward step and then backward, where you actually train the unknown parameters by calculating the gradients. You don't want to drive them to zero. And this is also a problem in the field because these functions, which are called the activation functions, which you see in every node, they can actually give a gradient with a close to zero. And there are lots of tricks to avoid that. But said that, this is the Hamiltonian which we implemented. And Arnaud, who was here yesterday, actually had a student, and they were the first who actually used this to study the Dutroux. And they got excellent results. And the Dutroux is actually a very not smart way to solve a two-particle problem, where you can actually set up a simple matrix in coordinate space and diagonalize and have the precision you want almost. But it was the first demonstration. And then Alessandro Lovato, who many of you may know, and he has actually applied this nuclear Hamiltonian where you have free body forces. This is a so-called pionless Hamiltonian. For those of you not doing nuclear physics, don't care too much about it. It's a simpler model for the nuclear forces, and it includes free body correlations as well, and free body forces. Ideally, what you would do then is to have, when you're setting up this model, so let me see if I can get the pointer. There would be a Slater determinant for the system. That's the way you bake in the symmetry, the anti-symmetry for the fermionic system. You may have a model for two body correlations, which should be this guy, doesn't see it. There we are, this one. And then you can bake in functions for three body correlations. So this is an exercise which is painful because you have to cook up models for it. And often you would calculate derivatives analytically. And you set up a new interaction, you cry for some time, you go down in your basement, you derive all the equations, and then you write a code. Actually, you don't do that, that's just stupid. You use automatic differentiation. So have you heard about automatic differentiation here, guys? That's a fantastic algorithm. That is the closest you get to painless dentistry. In the sense that if you want to calculate derivatives, it just is repeated usage of the chain rule. So you have a gradient you want to evaluate, you have a function, and automatic differentiation allows you to set up that. Actually, the back propagation algorithm, which is the central algorithm in neural networks, is automatic differentiation in what's called reverse mode. So nothing but that. So if you haven't read about automatic differentiation, look it up. That's really the day saver. It saves your day. Because calculating derivatives is not a thing which gives you deep insights, right? You've done it once, you know how to do it. You don't get more insights by recalculating it again. Okay, so these are the results. And this is a system where we calculated neutron matter. It's not infinite neutron matter, it's 14 neutrons in a box. And then with the length of the box, you can then assume that the density is translated into this one. So this is a low density nuclear physics system. You can do the same with electron gas, exactly the same exercise. In this case, you see the best Monte Carlo calculation, which are this one. These are the best Monte Carlo calculations. And you see now in a set of optimization steps with a neural network, we actually, the only input to the neural network, I'm not giving you all the details, but it's the anti-symmetry with a Slater determinant. There is the interparticle distance, relative distance, the spins, and the position of the particles, and there's a little bit more. But in essence, the network is actually learning the physics.
May I ask?
Yeah.
Do you get the sign problem here? Or not?
No, because this is variation of Monte Carlo. So there's no sign problem with the neural network because you're using the probability squared, not the wave function squared. So here there's no sign problem. So it's a variation of Monte Carlo where the neural network finds the optimal description of the system. Now, the problem with the neural network now is that it contains tons of parameters. And you may ask what is, yeah,
Usually, you're using probability just the function square, but the quantity you're calculating is oscillating now.
yeah, that's right. That's right. Yeah. I'm hiding some of the detail there. Yeah. Because else Fiorella will start punching on me soon. 5 minutes. Okay. Yeah, I'm done with the results soon. The thing which is interesting now is that since many of us are trained in, let's say, Hartree-Fock and variation of Monte Carlo, this is something we understand. These are just one particle, one whole correlations. And in a diagonalization problem, this is just a unitary transformation where you transform away a block of your Hamiltonian matrix. And you can then take the overlap between a Hartree-Fock calculation and the neural network, and perhaps that can give you some insight about what the neural network adds in addition to a standard network. So this is a kind of exercise which we are starting to do now, to analyze the physics. There's one way to do it, and this is back to what Marcello has been doing for many, many years, together with Umberto, Fiorella, and many of you people in Catania, and many others. This is a two-body distribution. And this is at low densities. And you see now that for the singlet case, so this is a spin 1s case, a spin 0. And this is a spin 1 case, and these are neutrons. And if your correlation function becomes large, that's a signal that, so the correlation function is just a distribution of two particles, so the two-body correlation function, distribution function, and that tells you about how correlated in a way two particles are. And if this becomes large, that's a sign. If you think back to the Ising moment, you know that when you have a phase transition, then all spins see each other, and the correlation function goes to infinity, diverges at the phase transition. So a typical sign of a phase transition is that this quantity here becomes large. Now, this is the non-interacting case. So this is with correlations and everything. So what it's telling you is that there is a clear sign of a phase transition going on, or the reminiscence of a phase transition in a finite system. In the triplet case, there's nothing, and you see the non-interacting case agrees fully with the full interacting case. But then the question is, why is the non-interacting case in the singlet case not zero? I'm going to leave that as a small problem to you guys. I'm not addressing the folks my age, rather all of you are basically younger than me, except Marcello. But think of why that's the case. We can discuss that. And you see also for the triplet case, just think of the terms of the anti-symmetry of the wave function. So triplet case, you have symmetric spin phase, anti-symmetric spatial phase, top part. Singlet case, symmetric spatial part, and anti-symmetric spin part. And there you have basically the answer. And then you increase the density, and you see that this is sneaking towards that one. And if you increase it more, it's getting closer and closer. So you see that you have a signal of a phase transition at low densities. And this is a way which I guess, Marcello, you've been analyzing these type of problems in terms of these distribution functions as well. And that is a kind of very nice tool to look at how two particles distribute in a medium. So that's a little bit back to what we discussed this week in connection with the birthday workshop here. And this is something you can now, so this is a neural network which you haven't told anything except the anti-symmetry of the wave function. That's the only thing, and the two particle distances. And there's a Hamiltonian, so the network is able to pick it up without you instructing it. And to me, that was a big surprise. This is the same for the electron gas. Gabriel is a student of Giuseppe Carleo, and Jane just did her PhD. And the same here. This is again 14 electrons, and there's a Wigner size radius, and you're basically spot on the best diffusion multipolar package. So I'm going to skip some slides here because I have something on Boltzmann machines, which is these generative networks. I will leave that out. And I'm also going to leave out, so you can actually look up there's a lot of activity going on error estimations. And Bayesian modeling, that's a hot field in machine learning applied to physics and actually many disciplines. I think there is actually a huge need for machine learning in physics. There's a lot of ongoing activities. My take on it is that this is a magnificent tool to attack multidimensional problems and multi-scale problems. That's the way I view it and why I think it's beneficial, because you have so many degrees of freedom that we have to, in a way, to try to reduce the dimensionality of the number of freedoms. So I look at this as a way to effectively reduce the number of degrees of freedom. And physics, by the way, is all about finding the effective degrees of freedom. That's the way I perceive physics. Then you can, the fun thing is that this is something you do with many other disciplines. It's a collaboration between mathematicians, computer scientists, the statisticians, etc., etc. There is a need for focused AI in accelerator science and experimental and theoretical programs. Here's lots of questions and probably many things I've forgotten. There are things like quantum machine learning, which is a very hot topic emerging. Quantum computing, obviously, not discussed here. And I think the investment in educational efforts is also something which I think is very important. And we as physicists, and now I'm putting on this kind of arrogant physicist hat, We actually been some of the leaders in developing many of these methods. And the kind of applications which have been developed, like if you look at convolutional neural networks, the way you tailor the filters to reduce the dimensionality is something which requires our insights about the physics. So when you do a recognition of objects, if you think of houses, you know that you don't want the color of the house because that's pretty homogeneous, but you keep information about the corners, the windows, the doors, and so on. So that's your filter. And then you would have to think of similar filters when you're looking at the physics experiments. So which are the quantities you're looking at? And that's where your insight comes in designing many of these algorithms and using them. Yeah, there's a lot of questions here. And one of the things which I like to challenge people with, because the particle physicists, they have actually made this Higgs boson challenge. And if you go to these websites like kaggle.com, there's a Higgs challenge. And everybody who wants to start with a physics machine learning project, they just pull down the Higgs data. And they try to beat the people at CERN in classifying the data. That's a useful case. And one can think of similar things for, let's say, nuclear physics, or solid state physics, or any physics discipline. It's a useful way to actually get started. Did I say something or? No. Yeah, we should stop. So if you wish to talk about education, which is uno dei miei cavalli di battaglia. This is really something that I can go from tangent. Thanks for coming.
Questions?
You say you speak about neutral matter. Actually, it's got team. So there's the problem estimated to face effect. Can you use machine learning answer for this problem?
We haven't done it. But that's a very good question. So what Marcello asks is, for those of you in the back there, so this is a box of particles, and you have only 14. So that means that surface effects are important, and you have periodic boundary conditions. And clearly they will influence the quality of the models. And we haven't treated them in the best way. And that has to do with computational efficiency. So this is a very important aspect. You could actually use machine learning to find out what are the best boundary conditions. Yeah, that's a good point.
Yeah, I have a question regarding the architecture of models.
Yeah.
And my question is that a priori, the architecture of models seems arbitrary, and the size of it and the structure of it seems arbitrary. And my question is about, are there any systematic ways to search for optimal architectures for a specific task?
So this is an excellent question because you're actually getting to the heart of the problem. So when you run this type of calculations, if you go back to a neural network, what you typically would have. So the model now is the architecture. So when you make a polynomial fit, the model is a polynomial. Now the model is actually the number of layers you have, the number of nodes, and the activation function which you give. And that is something which you normally would try with different type of activation function, different types of layers, till you reached an error which you think is acceptable. So there is no kind of a priori, except that what you normally would do when you look at the gradient training is that you would use methods because you don't know anything of the function you want to optimize, whether it is a convex function or not. So you would typically use methods like Adam, which is the one which has been proven to be the most efficient one. And then you would also try many of the other optimization. I should also say that there's a lot of research going on the way you calculate gradients. And some of you who may come from solid state physics may know a guy in Trieste called Sandro Sorella, and he has worked on a method which is called stochastic reconfiguration, but which actually is the same as calculating the Fisher entropy, which is a way to estimate this Hessian matrix, the learning curve. So that's a very interesting and ongoing research topic. So what you're saying, so in a way you can think of these as you running many numerical experiments. That's a very good question.
Yeah, I talked yesterday about CASOS, this new institute, which is for complex systems. My colleagues there, they have developed a MALA, a machine learning algorithm, and they speak about surrogate models. Have you encountered this term of surrogate models? Or something like they have very, so when you have more and more particles, the real calculations become more and more expensive. And somehow they, as I understood it, they test some machine learning, so some programs, which somehow emulate the results they obtain with the real problem, so that they can scale it then to many, many more particles. So 1 or 2 orders of magnitude bigger systems. So this is how I understood this is what they call surrogate models.
So I'm not familiar with that, but it sounds a little bit something parallel to what's called transfer learning, which means that you would train a simpler system and then you would use that as an input to a more complex system. So this is pretty common when you run an experimental analysis. You have simulation tools, so you have some theory. And you could use theory to generate data which you train a model on. And the hope then is that this theoretical simulation is close to the experimental results.
You hope you can scale it to bigger systems.
But I'm not familiar with that. I'm going to look it up.
Any other question?
First of all, thank you for your very nice talk with the knowledge you facing general machine learning as a tool. I mean, as a physicist, for several times I felt uncomfortable of do not have say much control on what really happens. From this point of view, my question is just in standard computer science, you have theory of complexity and you have algorithm and you can classify problems. Is there a way to have something similar in machine learning first, and what one may hope to change with quantum machine learning?
Okay, so if you think of the pre-deep learning methods, they are pretty well studied. Think of support vector machines, people know the stability of the methods, people know what you may expect from them. Many of these methods, the pre-deep learning ones, are really applied linearity and convex optimization problems. Now, when it comes to deep learning, I'd say that now the field of the mathematics of deep learning is emerging as a field of very, very big interest. And there's a lot of research going on, but in the present state, what you will often see is that people experiment with different segments, in different applications. And you will hear statements like, we know that stochastic gradient descent works best, but in our case, gradient descent works better, and we use that because we got a benefit. So you will see that type of statements, but at the same time, there are actually people trying to understand the mathematics of deep learning. So I would say at present, this is an evolving field, and there is not a precise conclusion. So that's the, when you think of quantum machine learning, I think that field is very interesting because, I mean, the idea is that you would apply this to quantum computers, and hopefully that could allow you to attack bigger systems. But at the same time, you still have the classical part, which would be the optimization part. So it would be a kind of mix of a quantum computer, and you call it a classical computer, which does the optimization. So it's still a field in interesting, but I mean, all the promise for quantum computing is still there as well. So that's the perhaps a superficial focus by somebody who is more a practitioner. Yeah, oh, sorry. Yeah.
Just if you can say a few words about education and how do you think this has an impact in the future?
Okay, this is a dangerous topic to end because now.
Just a few words to think about that.
No, I think. No, I think So if we don't give our students the computational skills, we are doing them a huge disservice. So we are not preparing them for the job market, for the future. So I'm a computational physicist and I've been teaching computational physics for 3 decades. And so I am biased, but I would say that if you cannot compute, you cannot attack any of these problems. So, and also I think it's important for the students we educate that they have a deeper understanding of what goes on. And so like when I teach machine learning, all the physics students, they're very dissatisfied with the way computer science teaches machine learning because that's taught like black box. They want to understand what goes on. And that's what we have to give to our students. So because our students are often going to be those who will develop the next generation of algorithms. So the kind of students we often meet are more the people who want to understand the black boxes. So I think, and I think if you look at that slide, which I put up here, no, not that one. It's not that difficult to actually revise some of the courses. We've been doing that, so you can incorporate these elements. We have many of these things already, so it shouldn't be so difficult if the department agrees that let's do it now. And go through the curriculum and just discuss where can we bring in this and these topics. And you can develop, if you think of a course in statistics, that can be revised so that you could include machine learning. You could have a own dedicated course on machine learning. That's fully possible. I think in simultaneously one could also think of having courses in quantum information technologies. One of the things we've been doing is actually in the bachelor degree is to have study directions option in quantum technologies, but also artificial intelligence and machine learning. So these are kind of, how to say, competences and knowledge, which I think our students should have. And in a way, we have to think of it as departments and how we actually revise the curriculum for the future. There may be some of the traditional things which we have to meet. So we often, when we teach, we obsess that they have to cover all and all of these topics, but maybe we should dive into more project-based type of learning. So this is something to discuss at the department level. So what I have here is just some small seeds. And what you see is that this is going on in many physics departments. So you guys in Catania, when I talk to Pino and many others, you're not the only ones who are thinking about this. And maybe one could relook at the physics program, the bachelor program, and the master program. So we in Oslo, we are actually going to change the physics bachelor program, which is called Physics and Astronomy, to Physics, Astronomy, and Quantum Technology. So name change is fully possible. And then we have study directions. And then we build up courses for these study directions. And you will, if you make a search, you will see that there are many other universities which have these. So that was a short answer.
A big problem.
But the thing which is nice, if you think of university, that I've been dealing with the curriculum development over decades. If you cook up something which people like, we have many colleagues which enjoy it. And a university setting is very interesting because we have the security net, we can experiment. And at the same time, if we come up with something which people think is meaningful, we have an extreme power in developing it.
Question. Very short. We applied some genetic programming to machine learning question to test some huge database, database from nuclear physics data. I would like to ask you a brief comment on the quality of the database that is needed to approach to attach with a machine learning study this kind of question to find, for example, feature dependencies on several aspects that is what you have said, discussed before.
Yeah, that's, you're really hitting at the core of the problem because the quality of the data and the amount of data
Yes.
is just essential.
The dimensionality of the data and the volume then.
You know,
We encounter several problems
yeah, yeah.
in that.
And in many cases, like if you run an experiment in nuclear physics or high energy physics, I mean, the data you have are the data you have.
Yes.
And you cannot get back and get new experiment.
But it could be useful, in my opinion, to find that if there is some wrong measurement, paradoxically. If you have a medium database, medium in terms of numerical quantity, you can find with your algorithm you can spotlight some measurement that could be in fault, for example. And this could be useful also to project the
So I have not worked with these topics, but what you're saying sounds very interesting. So I don't have any feeling for how it could be done. Sorry, I don't have a good answer to what you asked.
Thank you very much.
Okay, so I will thank you very much for joining.